So we are now in lecture number 9, and so far in the last couple of videos I have told you a little bit about conformities, different rock types, simple faults, and I have drawn them in a sequence, in a diagram, and I have told you how to decode it so that we have a general impression of the time. That means which occurs after, which occurs before, which is the oldest and which is the youngest. Sometimes there are ambiguities, but most of the time we can decode it with a reasonable amount of confidence. But that's about relative time. So today what we are trying to do is, tell you about how to determine quantitatively time. Details of this, those who are in geophysics possibly will not be knowing more, they will not need it. Geologists, of course, would require a lot of that, and so till that time I will just give you the essentials of how quantitative ages are determined in geologic systems. Now this is the idea of today's lecture number 9, which is called geochronology. Geochronology. So geo means, as you can understand, earth, and chron means time, logy means the science. So science of earth time, if you would like to have it that way. But this is a very, very broad field, a massive field. But I will only introduce you to how things work in nature. How do we quantify? Say, for example, we have said the age of the Earth is 4.5 billion years. Now, how do we know that? Age of the solar system is 13.7 billion years. How do we know that? So this is what we are trying to do, I will try to do at the moment. Try to tell you how age is determined in a geologic system with one example. Okay. Now in one of my previous lectures, I drew this diagram. Not I drew, the diagram was pasted from the internet. This was the number of neutrons, and this was the number of protons. So we were talking essentially about radioactivity. And we started that let there be a parent with NP coordinates. So this parent with an NP coordinate, it could decay by what is called beta decay, which would mean losing an electron. If it loses an electron, essentially, then you have a neutron becomes a proton. So essentially what you have, your number of neutrons decrease, but your number of protons increase. So if you have it, then you will have n minus 1 p . Yeah, just a little confusion. Am I being right? No, I'm completely wrong. So it would be something here, n minus 1 and p plus 1. This would be the position of the daughter if there was what is called beta decay, which means that a particular element loses an electron. If it does so, then one neutron changes to proton. So you have n minus 1 and p plus 1, and this is the daughter of a parent np, and this is beta decay. But if you have electron capture as one more important process, as you know it happens, then the reverse obviously happens. If it's an electron capture, then that electron combines with the proton to form a neutron. So you increase the number of neutrons, but you decrease the number of protons. So you will have n plus 1 and p minus 1. And this happens if you have something called an electron capture. And finally, what you have is an alpha particle decay, which is essentially a nucleus losing 2 protons and 2 neutrons. So if that is so, then here it is. It should be this way and this way. Here you have n minus 2, p minus 2, and this is essentially going this direction. It's alpha particle decay. This is called alpha particle. So we have beta decay, 3 natural processes by which an element, this we have discussed before, where an element in the unstable field would try to move into a stable field. And that it can do by beta decay, it can do by electron capture, and it can do by alpha particle, decay of an alpha particle. So these are the 3 different processes. As you can see that it is a play between the neutrons and the protons. And now we will go and see what happens. We will talk a little bit about radioactivity and see how things move on from there. So essentially, radioactivity would involve a parent nuclei N0 and a parent nuclei which is a 0 here, and you have time increasing. So this is n increasing. N essentially here is the number of parents. N here is the number of parent nuclei. So normally what happens, this is about 100% and this is about 0%. So if you have the decay goes on this way, it has been proved experimentally and theoretically, the decay moves in this direction. The decay happens in this direction. So as there is time, as more and more time progresses, you can get the word now, as more and more time progresses, the number of parents decrease and the number of daughters gains. So now you can imagine a little bit, you're bringing in the variable time, and here you have a parent-daughter isotope. So technically, if you can measure for an element the ratio of the parent and the daughter, then technically you should get an handle of the time. This is the basic logic for any chronological systems. That if you can find out the ratio of the parent and the daughter, then it should give you an handle of the time elapsed. So this is very, very important in geology. Time elapsed. You see, when n is equal to n0, that means 100%, all of them are parent. Your time t is equal to 0. And when this curve of the parent becomes asymptotic, and this time t here is now. So when we have this time, it is from time 0 to time now. Now this is an important concept. When we say the age of the earth is 4.55 billion years, I mean from that time till now, it's 4.55 billion years. Or if I say you are 20 years old, which would also mean that from the time of your birth, now it's 20 years. Similarly here, this time is essentially called time elapsed. It's not something going forward, but going backward. From backwards to now. Right? Now there is a famous equation given. So this is essentially for the parent, which we will label as P. And this curve is essentially for the daughter, and we would say this is D. We will bring in these two terms a bit later, but for the moment, this is for the daughter element and this is the parent element. The daughter element increases, the parent element decreases, and if you know the parent and daughter ratio, you should get a handle on the time elapsed. An important aspect in this is called half-life. Now all of you know this, so I don't have to dwell into it great. Half-life is where it is half n0. So this is the point, it's half n0. And when a particular parent nuclei loses half of its mass, at this point, this time is called half-life. T half. Now this you all know. Another point is 1/4 n0. What is this? Half of half. So this is T1/4. So you can have you have smaller and smaller numbers. But we take T half, which is called the half-life, when a particular nuclei loses half of its mass due to decay. The time taken, or this time, the time elapsed, is called T half. Now this curve is given by this very famous equation, which you all know, is minus lambda n. This is a very famous curve, all of you know it, that the change in the number of parents by time, the first derivative, is equal to lambda, which is called the decay constant. And n is the number of parent atoms still remaining. So that is how they are related. The negative value is because if this decreases, then the opposite happens to the n value. This you all know. We will start from this very, very famous equation and we will see where we go from here. So we start with this equation. dn by dt is equal to minus lambda n. Now most of it you know till a particular point, and then we will come to an unknown domain for you. And then you can write dn by n is equal to minus lambda into dt. And then you can make integral of this. So here time t is equal to 0 till time t is equal to t, and n is equal to 0 to n is equal to n. So this is how the integral goes. And for this you will have ln n by, I will just check it out, by n0 is equal to minus yeah. So, yes, sir. I got a little confused. So t minus 0 is equal to minus lambda ln n by 0. Now you must understand lambda is independent of time, and therefore this is taken out. So we have this situation where we can write t is equal to minus lambda ln n by n0. This is the equation that we have. And from this, now we can write t is equal to lambda ln n0 by n. So from here we have n by n0 is equal to e to the power minus lambda t. This is what we will have. And then we can have ln n by n0 is equal to minus lambda t, and you can have 1 by 2, because remember 1 by 2 is equal to minus lambda t half. You see, that's half-life, because then n by n0 is equal to 1 by 2. And then if we do this, then we will come to this very famous relationship that you have is t half is equal to 0.693 by lambda, which gives us a relationship between lambda and the time elapsed. T half is equal to 0.693. This is one of the very famous reactions which you have all studied in school, and this is what it is. It gives you a relation between half-life and the decay constant. 0.693 is nothing but ln by 2. Okay, but another equation is derived, and that is more important to us. And this is this equation. N by n0 is equal to e to the power minus lambda t. Or we can write n is equal to n0 into e to the power minus lambda. Now if you do that, if you go back and check, essentially your n is nothing but the number of parents, and your n0 is equal to parent plus daughter into e to the power minus lambda. Now this translates to P into e to the power lambda t minus P is equal to T. Which would mean, if I take this equation up, D is equal to P into e to the power lambda t minus 1. Now that is an important equation. That the number of the daughter elements would be equal to the number of parents into e to the power lambda t minus 1. Now you can imagine if t increases, this value increases, and therefore the number of daughter increases, although the p decreases. So this is a fundamental equation that we will be taking for further discussion. So there are essentially two equations. From this very basic equation, you can derive two very important equations. One is this equation, that the number of daughter element is equal to the number of parent element into e to the power lambda t minus 1. That's one good equation. And the other equation which you knew before, that you have t half lambda is equal, the relationship between the decay constant and half-life, that t half is equal to 0.693 by lambda. These are the two important equations that you derive. We will use for geochronology, for finding out time, we will use this fundamental equation. I will give you just an example. We will take a very simple decay equation. We don't go into too many complications. We got to see what is the logic is. Now, you have heard about two elements, rubidium and strontium. Rubidium has several isotopes and strontium has several isotopes. Now what happens, in naturally occurring rocks, some of these isotopes occur in higher concentration, some of the isotopes occur in lower concentration. Some of the elements, some of these are radiogenic, that means they either decay or form by decay. Some are non-radiogenic, that means they are not related to a radioactive decay process. So once you have them, you have them. You don't change them anymore. No way by radioactivity. So you have radiogenic process related to radioactivity or non-radiogenic elements which are unrelated to radioactivity. Now, 87 rubidium is an important isotope of rubidium, and this on beta decay breaks down to 87 strontium. This equation is a beta decay equation. For understanding much of the equation, I leave it to you. You have to read. So essentially what we have, 87 rubidium disintegrating into 87 strontium. This is how the disintegration occurs. And this is a beta decay. So 87 strontium is radiogenic. This is the daughter and this is the parent. Here, this is the daughter and this is the parent. Now, so you have 87 strontium. So now you'll have imagine that you have a rock. Let's say Earth. When Earth formed, let's say at a particular point of time, the Earth incorporated all these different isotopes radiogenic and non-radiogenic elements, isotopes. Radiogenic elements is which changes their abundance with time. Non-radiogenic elements do not change their abundance. So when the Earth was formed, it accreted some amount of 87 rubidium, which immediately is unstable. Remember the neutron capture process. This is a neutron capture process and there's a beta decay. So it immediately started to decay. And you had 87 strontium being produced. But the rock also had incorporated, when it formed, it also had 87 strontium, which it had inherited not by radioactivity, but as an independent amount it incorporated. So what happens in the total R, if you take the 87 strontium, if you say it's total, then there was 287 strontiums. One was 87 strontium initial. That means this is the strontium the Earth acquired by birth. It is something like my DNA, for example. Certain things I have acquired by birth, and certain things I have acquired from the surroundings. So this 87 strontium initial, this was incorporated, it was incorporated by Earth, or it could be incorporated by a system, but also it had extra 87 strontium because it had incorporated 87 rubidium, which produced 87 strontium, which is radiogenic. Have you understood? So this strontium was produced from 87 rubidium. Over time, the amount of strontium increased over time. But there was an 87 strontium initial, which a system or a Earth or something that you want to take was incorporated already. So your total strontium has 87 strontium initial DNA, 87 strontium radiogenic, which is acquired over time. This is equivalent in your life to your experiences that you acquired since birth. So you have your DNA, what you are is the DNA that you acquired through your birth, from your parents, like I have inherited. And the other part is you have inherited certain aspects and attributes from the surroundings. This is from the surroundings. This is by birth. Have you understood? These are the two different 87 strontium. So if I finally write an equation then, and remember this is the daughter, so I can write now from this expression 87 strontium is equal to 87 strontium initial plus 87 rubidium into e to the power lambda t minus 1. Yes or no? Because this 87 strontium here that will be produced, this is 87 strontium. This will be essentially 87 rubidium, which is the parent, into e lambda t minus 1. Have you understood? So this is what it is at the moment. So we have this equation, 87 strontium, the value that you, today for example, you take a rock and you put it in an instrument and you measure 87 strontium. This is the value that you get. But it has two components. One component is the 87 strontium it inherited during growth, and another is another part of 87 strontium which it inherited through radioactive decay of its parent 87 rubidium. So what happens normally during this analysis, which are quite sophisticated analysis, which require, for the moment it should require very great amount of cleanliness, high amount of sensitivity, everything included. Instead of measuring the abundance of the element, it is better to measure the abundance of a ratio. So what we do normally is, in this, you divide it by a common divider. Common divider. That means that number should not change with time. And one convenient isotope is 86 strontium. Now 86 strontium is non-radiogenic. So we know that the concentration of 86 strontium does not change with time. So if I divide this whole equation by 86 strontium, then essentially I don't change anything. But why am I doing it? Because it's easier to measure the ratio, isotope ratio of an element, rather than measuring the absolute abundance of the element. Technically, that is why the isotope ratio is measured by what is called, the instrument is called a mass spectrometer, which separates, its elements are passed, and as materials are passed through a magnetic plate at very high velocities, and then because of the magnetism they separate into different weights, so you can find out the ratios much more accurately than finding out the individual values. So if you divide it by 86 strontium, then you have 86, 7 strontium. I will erase this. This is already clear, so we can erase this. Because I will need a part of the board. So essentially this equation becomes 87 strontium by 86 strontium is equal to 87 strontium by 86 strontium initial plus 87 rubidium by 86 strontium E lambda T minus. Now I have written this initial. It does not matter because this 86 strontium is also initial. It does not matter. This value and this value are not different. Only thing, this ratio is the initial ratio. That is why the whole thing is put under what is called initial. But there is no numerical difference between this value, 86 strontium value, and 86 strontium value. So this is the final equation that we come to for the decay of 87 rubidium to 87 strontium by beta decay. Now there are certain important things. This is an equation of a straight line where this is called y is equal to c plus this is x and this is m. This is the equation of a straight line. Let me show you. We take graph. This is x-axis, 87 rubidium by 86 strontium is the x-axis. And in the y-axis, you have 87 strontium by 86 strontium. To the y-axis. Now, in a rock, you have, say for example, if you have a rock which you're trying to date, you have different minerals. Have you understood? Say mineral A, B, B, C, A, C, and so on. And you have the final rock. So what happens when the material formed, they had different 87 strontium, they had the same 87 strontium and 86 strontium, but they had different 87 rubidium by 86 strontium ratios. So let's say I start from here and you have A here, say B here and C here, and your rock, which is R, let's say the rock is here. So with time, what will happen? 87 rubidium will decrease and 87 strontium will increase. So every point in the graph will move in this direction. This happens when time t is equal to 0, during when the material formed at that point of time t is equal to 0. A was characterized by this value of 87 by 86 strontium, but a different value of 87 rubidium, different value. Obviously, the rock will have an intermediate value depending upon the proportion of A, B, and C, etc., etc. But immediately after the formation at time t is equal to 0, 87 rubidium will start disintegrating into 87 strontium. And finally, according to this equation, you will have this situation. At time t is equal to t. What is t now when you're measuring? You're measuring this value. Have you understood? This time now. And this is the time when this formed. This is the time now when you analyze. It could be yesterday, it could be tomorrow, it can be the day after. And this is the point A prime, B prime, rock prime, and C prime. Technically, if you have a closed system means, thermodynamically, you will have something called a system and you will have something called a surrounding. So you have an interface between what is called the system and with the surrounding. When there is no mass transfer, but only energy transfer, then this is called a closed system. So in geochronology, the important point is that if the system behaved as a closed system, means there was no migration of isotopes across the interface, because that would change the values. So assuming closed system since its formation, you can think that how can this be done? It can be done. It can be done. That since the formation of a particular meteorite till today, when you analyze, it can be said and it can be proved that whether the system has behaved as a closed system, but if it has an open system, that means the isotopes that you measure now are not a part of the closed system. Some could have come in later and some could have gone out later. One proof will be all the points should lie on this line, and this line is called an isochron, because here time is the same, isochron. So it should lie on this isochron. If you see that the points are scattered, then also you know that your system did not behave as a very good closed system. It never behaved. Have you understood? So what happens at time t is equal to t, all the lines should both lie on the same straight line if the system had behaved as a closed system. Now you can see that this line, once you plot the graph, 87 rubidium, you will have this line and you can find out angle theta. So that is tan theta of that is equal to the slope E lambda t minus 1. That means your tan theta plus 1 is equal to E lambda t or ln of tan theta plus 1 is equal to lambda t, or you can see, if you know the lambda values, the decay constant of, in this case, rubidium strontium, if you know, then you can quantify time. That is the important point. That means that in this equation, the slope of the equation is a measure of time. You can see this line from a horizontal position slowly move into this position. So this angle theta essentially is a measure of elapsed time. So using this equation, the slope value and the decay constant, the time elapsed can be determined numerically. This is how time is measured on natural rocks. Now, there are many available such isotope systems which are available now. Many of them could be applied, but they have different half-lives. So depending upon the half-life, you can apply it only to specific time zones. Say, for example, I give you a question, why, and you write it down, why doesn't carbon dating is not done to measure the age of Earth? Why is not carbon dating used to measure the age of the Earth? But at the same time, rubidium strontium dating, as I have shown, is used to measure the formation of the Earth, planet and meteorites, but it is not used to measure the age of a planet. Why not? I think I leave this to you, that why is the half-life so critical, and how does it determine whether a system can be extended to this time or that time or this time? Like I said, why can't carbon dating be used for finding out the age of formation of the Earth? And why can't rubidium strontium dating be used to find out the age of a plant or a dead body or a burnt out or a wood from a burnt out forest? Why can't it be done? Try to find that answer out. Now this is an eventual equation where you can see the slope of the isochron is essentially, the tan theta of it is essentially a measure of the total amount of time. But what we have not done is, when you do the regression line of the points on this and you find out the value of C, what does it tell you? It also gives you a very important information. For example, for me, if they have to find out my biological parents, they are not here now, they are dead long back. My biological parents, it would be very good to check my DNA and theirs. That's a wonderful proof to check it and cross-check it. So, when you get this value of 87 strontium, 86 strontium initial, you get a measure of the chemical environment during which this particular system started to form. It gives you the environmental constraint, in this case 87 by 86 strontium ratio. What was the ratio of the gas from which the Earth formed? So the intercept C, this intercept tells you about my DNA, about the chemical environment in which a particular system was formed, and this slope of the equation, of the isochron equation, gives you a measure of the time that has elapsed. There are, as I said you, there are many available systems, and the half-life determines how old can you date an event. How old can you date an event? And I've asked you to read about it. Okay, I stop here for now. So what we have seen over the last few classes is, I taught you about different rocks in very elementary way, igneous sedimentary metamorphic rocks. Then I taught you a little bit about unconformities in ocean surfaces. And then we told you about several faults that can disrupt the rock. And then we put them into a geologic section and tried to find out geologic time, relative time. But we never got hold of what was the actual magnitude of the time. Whether it's today, is today, billions years ago, how many billion years ago, that we did not know. These isotope systems, not this one, like this many isotope system with many applications, they can be used to find a date of a particular event. And it's you to find out how half-lives are important to choose whether certain rocks can be dated, how old the rocks can be dated. Why is it important? I leave it to you for your own reading.